Today we're going to look at the 6-6 Day 3 notes. To introduce the topic, I have you evaluate different powers. 4 to the 4th power is 256, but so is negative 4 to the 4th power. If I had you evaluate 4i to the 4th power, well, we already know that 4 to the 4th power is 256, but I to the 4th power, you can think of as I squared times I squared, or negative 1 times negative 1. Notice that this would also end up being 256. And then if I had you do negative 4i to the 4th power, it would be the same situation. Now, in conclusion, the fourth roots of 256 are 4, negative 4, 4i, and negative 4i. In the past, you guys have solved things where I said, hey, x to the 4th power equals 256, and you've taken the fourth root of both sides, but you've only given me plus or minus 4 as your solution. And maybe some of you thought about this and said, well, wait a second, degree 4, I should have 4 total solutions. But unfortunately, from what you've done in the past, you have only been finding real solutions. Now, maybe you thought that these were double roots. Oh, good. I'm so glad my dog is like deciding to clean himself right now, right by the iPad. Go away, Burley. He'll be back. You've only been finding the real solutions. Now, you may have thought, well, maybe these are multiplicities. Maybe these are double roots, but they're not. Actually, 2 of these solutions are imaginary. As you can see right here, we have 4i and negative 4i. Now, when you learned how to factor x to the 4th minus 256, you may have seen that this can be written as x squared plus 16, x squared minus 16, and you would get those solutions by setting those equal to 0 and getting both the real and imaginary. But had you not factored, you would have only provided the real solutions. So today, our focus is going to be finding all roots of numbers. So if it says fourth roots, I need 4 different solutions. They will be both real and imaginary. And we'll be taking roots of numbers that are imaginary themselves. So that is really what we're doing today. Now, if you graph each of these roots, 4 is a real number. It would go right here. So 1, 2, 3, 4. If you graph negative 4, 1, 2, 3, 4, go right here. If you graph 4i, we'd be on that imaginary axis, and then negative 4i would be right down here. One thing you should notice about the roots of a number is that, he's still shaking, the nth roots of the complex number are equally spaced on the complex plane. And this will be true always when we're doing these problems. So to show you this idea of equal spacing, for this first problem on here, it said 1/6 root, which means 6 total solutions is 3 kiss 10. Find the other 6 roots. Well, to find out how they're equally spaced, we're going to take 360 degrees and we are going to divide it by 6. Because there's 6 total solutions, they're going to be equally spaced on the complex plane. So if I take 360 and divide it by 6, I get 60 degrees, which means I will have a solution every 60 degrees away, which means that for my first solution, so this is root 1, for my second one, I'm going to keep the 3 in the front the same, but I'm going to add 60 to 10 and get 70 degrees. For my third solution, I'll have 3 kiss. I'm going to add another 60, and that's going to give me 130 degrees. I'm going to add another 60, and that's going to give me 190. I'm going to add another 60, and that's going to give me 250. And then I'm going to add another 60, and that's going to give me 310. Notice if I add another 60 to that, I'm at 370, which when you subtract 360, takes you right back to that original 1. So this is the idea of equal spacing. Now, for today's notes, this is going to be a very involved process. We're actually going to be, I'm going to have to go back and fix this before you guys download this. This should be day. Oh, wait, is that right? Hold on. Oh, wait, no, we're good. All good. No issues. What? I didn't make a mistake. So what we're going to be doing today is starting off by getting a complex number and writing it in trig form. So that was our day one materials. We're then going to use de Moivre's theorem to find one of the roots in trig form. Now note, this looks different than the de Moivre theorem that you learned. But if you rewrite this, keep in mind that this is r KISS theta to the 1/nth power, right? Because this is a root number, so if I swing it around, I would write that as 1 over n. Now, this is no different than it being n in the sense that I would still say r to that power, and then I would take the angle and multiply it by that value. So you're just going to see, though, instead of it being a 2 up there, it'd be a 1/2. And so the process still stays the same with de Moivre. It's just that following de Moivre, we're going to use this equal spacing idea that you just learned in the day 3. I thought that's where that lesson 6.6 day 1, not to justify why I said what I said earlier, but this part right here is the day 3, that equal spacing. And then going back to the day 1 notes, we are going to write our final answer in standard form. So you're going to see very involved. Starting with the first problem on here, it says find the 6th roots, which means 6 total solutions. So when you are done and you are circling your final answers, you should have 6 of them. Now, you're given cosine 3 pi plus I sine 3 pi. Well, first of all, let's simplify this. If you go to 3 pi, well, remember, by subtracting 2 pi, this is really the same thing as pi, as is this. Now, if I say, what is the cosine of pi? That's -1. If I say, what's the sine of pi? That's 0. So really, we're finding the 6th roots of -1. What? That's really the same thing as solving x to the 6th equals -1. And now find every single solution that when you raise it to the 6th power, you get -1. Now, a lot of you are saying, what? You can't do it, because you're thinking 1 to the 6th power wouldn't work, -1 to the 6th power wouldn't work. That means all 6 of these solutions are imaginary. So you can see kind of the complexity of this. Now, if you want to think of it this way, think to find x, to find each of these solutions, we're really taking -1 and raising it to the 1/6 power. Because remember, we're taking the 6th root of both sides. The problem here, though, is that this needs to be written in trig form. If we want to use de Moivre, -1 is not in trig form. We need to get this in trig form by thinking about graphing this. If you graph, remember that this is your real axis and this is your imaginary. To graph -1, I would go right here. Well, to get that in trig form, think about what your r value would be. What is your distance away from the origin? Well, it's just 1. What angle are we at? Well, think about over here, this is what we call pi. So really what we're trying to solve right now is 1 KISS pi all raised to the 1/6 power. So notice now I am in trig form. Now, once you get this in trig form, I can use de Moivre. De Moivre says to take that number in front and raise it to that power. And then we're going to take the angle and multiply it by that power. So 1 to the 1/6 power is just 1, but then we're going to get the KISS pi over 6. We just did all of this work and only found our first solution. So this is star sub 1, because that's our first solution. So that means that we still have 5 other solutions to find. Well, how are we going to find those 5 other solutions? We're going to use equal spacing. Now, let me change my color just so you can kind of see that that was really the first part of the process. Second part of the process is to think about equal spacing. Now, since I'm in radians, I'm not going to take 360 and divide it by 6. I'm going to take 2 pi and divide it by 6. And you may say, why 6? because there's 6 total roots, which means I'm spacing 6 total answers on the complex plane. That means every solution is pi over 3 radians away. You actually might want to leave it as 2 pi over 6 though, because spacing, you're going to have a common denominator by doing that. So we found star sub 1. If I want to find star sub 2, my second answer, I'm going to leave the 1 kiss, but then I'm going to take this angle of pi over 6, and I'm going to add that 2 pi over 6 to this answer. So my next answer here, when I add 2 pi over 6, is going to be 3 pi over 6. I'll reduce that at the end. Let's go to a different color, green. My star sub 3, I don't know why I'm doing stars with subscripts, is going to be 1 kiss. Now take that 3 pi over 6 and add 2 pi over 6. That's going to give you 5 pi over 6. And then we can keep going. We can get star sub 4. I've never used this notation before, so it just makes me laugh. And then I'm going to get the 7 pi over 6. Because again, I'm adding that 2 pi over 6 to each of my answers. And then I'm going to go brown. I'm going to get 1 kiss, and then this will be my 9 pi over 6. And then we have one more. I don't know if I did green. 1 kiss, and then that would be 11 pi over 6. Notice if you add another 2 pi over 6, that's going to take you to 13 pi over 6, which is equivalent to the first answer of pi over 6. So those are all, oh, I did go green. Oh, it's okay. Those are all of your different answers, but unfortunately, these are not in the correct form that we want them. So in order to get them in the correct form, we now have to use our unit circle to write these in standard form. So going back to this answer, think about the ordered pair for pi over 6. You can even write out each answer separately. Cosine pi over 6 plus I sine pi over 6. Think about pi over 6. The cosine there is root 3 over 2. The sine is 1/2. So what I end up getting is just the root 3 over 2 plus 1/2 I as my first solution. Which is crazy, because that means if you take this quantity and you raise it to the 6th power, you're going to get a solution of -1. And I can actually show you how to check that in just a moment. Same thing with this next one, 3 pi over 6. Now we're going to want to reduce. That's really pi over 2. To make a shortcut, I've seen some people actually just write the ordered pair for this pi over 2. So if you think about pi over 2, that's over 0 up 1. But then don't forget that the sign value would have to have the I with it. Sometimes seeing this kind of throws me off, so I don't do it that way, but just something you can think about. And you would get for your answer the sign value there, which is going to be 1. So you would just get 1 with an I. But again, for those of you that want to see that work, see that it just throws me off. So I'm going to say 1 cosine pi over 2 plus I sine pi over 2. And then this right here is 0, and that's 1. So that's where you just get this 1I or I. Now, for this next answer, if you think about pi over 6, the first answer that we found, and you think about pi over 6, this actually has the same ordered pair, but the only difference is that when you're at 5 pi over 6, the x value is negative. So just take the answer we got for the first one and just make the x value negative, but keep your y value positive. Because again, if you go to your unit circle, you're going to see that pi over 6 and 5 pi over 6 have the same ordered pair, just the x value changes in sign. Same thing with 7 pi over 6. It's going to have the same ordered pair, but this time, since 7 pi over 6 is down here, you're going to see that both the x and the y value are negative. So it's kind of like a cool little shortcut with these. Is it bothering some of you guys that I'm writing on this line? Because it's kind of bothering me, but I'm just going with it. Maybe it's not bothering you, or was it, but now it is. For this answer here, reduce this by 3. You're going to see that this is 3 pi over 2. And kind of going back to that answer that I got in blue, it's going to be the same thing, but now the sign of 3 pi over 2 is negative 1. So this is just going to be negative I. Oh, let's go brown. And then finally 11 pi over 6, just like 7 pi over 6, you're going to see that this is going to have the same quantity, but because you're in quadrant 4 for 11 pi over 6, the x value will be positive, but the y value will stay negative. So those are your 6 different solutions. Really cool thing that you guys can do is you can actually check your work. So if you wanted to check your work, you could do the mode of your calculator, and you can go to this a plus b. Oh, well, how do I not do that? Okay. You can go to this a plus bi form, and when you go to your home screen, you can type in the square root. Let me do parentheses first. Parentheses. Square root. I give up. Oh, God. Square root of 3 divided by 2. And then you can do plus 1. I'm going to put this in parentheses. Divided by 2 with an I. Now, there's an actual I button in your calculator. If you guys look by the bottom, by where 0 is, to the right of it, above it, there's an I. You have to hit second first, though, and then that'll pop in an I. So it's that period button. If you put all of that in parentheses and you raise it to the 6th power, notice that you're getting this value here, which is equivalent to what we got right up here, this negative 1. Because note that 1e to the negative 13i is basically 0. That's a 1, and then move the decimal place like 13 units to the left. That is actually equivalent to 0i. And then you can do the same thing with just I. So if I take parentheses and then I, and I raise that to the 6th power, you'll probably see it better here. You get that negative 1. Same thing with that one. These are all kind of, with the radicals, or that's where you're going to get that E part with that because of the radicals. But if you do negative I, and you raise that to the 6th power, you're going to see that that also gives you negative 1. So pretty cool that you can check those answers just by raising that quantity to the 6th power, and you should note that you are getting negative 1 in all those cases, even when there's that scientific notation, because remember, that really means this number right that was given to us really means 0 times I. Okay, so looking at the next one, you guys are going to see that the next problem asks you to find the cube roots of negative 27i. So to start off, I'm going to think about this either as x cubed equals negative 27i, or just go straight into it. But if it was like this, and you're finding the cube root of both sides, this is equivalent to thinking of negative 27i to the 1/3 power. Now, write yourself a note. We want 3 total solutions for this problem. So when we have a problem like this, where we have the negative 27i to the 1/3 power, we have to do step 1 of getting this in trig form. So to get this in trig form, we're going to do a quick sketch. Remember that this is your real and this is your imaginary axis. Negative 27i would graph somewhere down here. So think your r value here is 27. That's your distance away from the origin. And then your theta is going to be 3 pi over 2. So once we find those values, we can write this in trig form, which is our step 1. But then we need to use de Moivre's to find what our first solution is. So again, this is not our first solution. Common mistake is that people forget to actually do this part, which is very important because that's how you get that first solution. So we're going to get this 27 to the 1/3 power, kiss, and then 3 pi over 2 times 1/3. So 27 to the 1/3 power is 3, kiss, and then when we multiply here, we can cross cancel, pi over 2. This is actually that first answer, but in trig form. I'm just going to go with that notation. So star sub 1 is 3 kiss pi over 2. Now, to find your remaining two solutions, we need to do equal spacing. So again, we could take 360 or take 2 pi. Since there's 3 solutions, we're going to divide that by 3, and that means every solution is going to be equally spaced 2 pi over 3 units away. So that means that I can take that first solution, and to get to the second solution, I am going to rewrite the 3, let me put a notation there so you can see the separation, 3 kiss. Now I need to take pi over 2 and add 2 pi over 3 to it. So you can think in terms of common denominators. This is really 4 pi over 6. And if you think about pi over 2, that would really be 3 pi over 6. So that means my next solution here is going to be 7 pi over 6. And then my final solution, if I add the 4 pi over 6, you're going to see that that's going to give me 11 pi over 6. Now, to conclude this problem, we now need to use our unit circle to find each of these in standard form. So what you're going to see is that if you go to pi over 2, you can write this out, 3 cosine pi over 2, I sine pi over 2. Cosine is 0, sine is 1. You're just getting a solution of 3i for our first solution. And then we can go to the next one. Remember 7 pi over 6, we'd recently done this one. Remember that 7 pi over 6 is going to have a cosine value of negative root 3 over 2. And then your sine of 7 pi over 6 is also going to be negative, but negative a half. So you're getting the solution of negative 3 root 3 over 2 minus 3 halves I. And then finally this last one, luckily we're seeing the symmetry again. 11 pi over 6 is going to actually have the same ordered pair as 7 pi over 6, but the x value will be positive and the y value will remain negative. So at this point, I'm going to stop the video. I would like for you to see if you could do 4 and 5. I will start up the video. I'll create another video with me showing the work for all of these, but I just want to see what you guys can do first. And there are some you try on the own as well at the end. So I really want you guys to try to finish the notes from here, but I will post videos to go through just to make sure you can get that feedback if you are understanding this topic or not.